Testing, testing. Okay, our last lecture on geometry is more or less a summary. I wanted to do a couple of applications on geodesics, shortest lines in a curved geometry, and also talk a little bit about the mapping problem. Now, the mapping problem you're all familiar with, and that is what you want to do is you want to take a two-dimensional surface, maybe with a coordinate system, and you want to take a three-dimensional surface, say the world, which is a sphere, or very close to a sphere, and what you want to do is you want to take, say, and this will be pretty bad, I'll try to draw North America on this sphere here. So, okay, so here's Alaska, Baja California, Mexico down there, and then let's do the Gulf, Florida up here, then maybe have Bay of Hudson and Canada, etc. So this is North America. It's actually not too bad. And then here's South America, etc. So we have a three-dimensional world that we live on, and we want to map that onto a two-dimensional plane, which we call a map. So in general, if we have coordinate systems on the world, we want a mapping that takes, say, two coordinates that may not be rectangular, x and y. So let's just map it to three-dimensional. So this is in R3, it's a surface, and this is on a R2, which will be our map. Now by map, I mean the literal map. I mean the kind of map you'd look in National Geographic or whatever. Now, what you'd like to do is to preserve areas, angles, distances, etc. So what you really want is an isometry, which preserves distances and everything else. Angles, areas, etc. But unfortunately, Gauss proved that the following, that if you have two different surfaces with different curvature, Gauss curvature, then you could not have an isometry. So if the curvature is different, then you cannot have you can't have an isometry, so no isometry, which means you cannot have what amounts to a perfect map. You can either preserve areas or you can preserve angles, but not both, if the curvature is not preserved. So you have preserved areas or preserved angles. Now, the Gauss curvature of a surface here is 1 over r, or 1 over r squared, where r is the distance of the Earth. So the Gauss curvature in this case is 1 over r squared, and the Gauss curvature here is 0. Now, if you look at the difference between 1 over r squared, where r is, 8,000 kilometers or something, in terms of meters, that's a pretty small number. So if you had a finite, and of course that would be putting a map on, the size of the Earth. Now if you shrink the Earth down to like a globe, and are trying to do, say, a 1 meter globe, this now becomes fairly significant. So what you end up with is you end up with a distortion. So going from And you've all seen these kind of maps that one of them, I forget which map it's called, breaks the thing into sort of like orange peel slices and strings them together like this. Then you have all these different projections. Now, when you go to some of the other links, we'll see there's the Mercator projection. There's a bunch of projections that create maps. So the projection, particular details of the projection, define the map. Now, the link here, let's see if it's the first one or the second one that I want to do. Okay, so this is a Maple, a link to a Maple. You can see it's coming from mapleapps.com and Maple Maps. So I'll show you where that application is in just a minute. But this is a version of, HTML version of a Maple code, because you can see the actual Maple stuff down here in a little bit. But there are a surprisingly large amount of map projections. There's hundreds of them that have been developed through the ages. And there are actually some references in here. Some use sort of exotic coordinate systems, etc. Maple has built into it some commands, for example, add coordinate and change coordinates. And those functions, it's easy to create some of the simple map projections, but this particular one has extended Maple's library to a much more sophisticated one. And so they actually bring in their own libraries. I tried downloading this and I was not able to get it to function. There's a problem. This is a Maple 5 library and it seems to have trouble initializing it. So I'm going to try to see if I can find a version of this. It's quite an impressive system here. But what you end up, they have actually 186 bodies which are coordinatized and digitized. So index 0 is actually the coastline of Europe, Africa, and Asia together. That's a fairly large piece of data. The shoreline of North and South America is the second element of this array. Australia is 4, etc. So this is an example. This is actually let's see if it's a one-dimensional or a two-dimensional graph here. I guess that's actually an HTML, so it doesn't count there. Now there are some links to other things in here. If you want to talk about cylindrical projections, azimuthal projections. I might notice that there is a projection that does preserve. If you look at this and then you look at a cylinder, if you take the edge and just wrap this and glue it around, you can take a piece of paper and draw a line on here and it will curve along like this, and you can actually, it will preserve areas and angles. So this is an isometry because the curvature of the cylinder is 0. So the curvature is 0 here, and the curvature is 0 here, and so you do have a mapping that you can preserve angles and areas. But not too many people want to have, we don't live on a cylindrical Earth, so we do have some deformation here. So the cylindrical projections are here. Let's see if they have some pictures here. So here's the Mercator projection here. And then they have some other projections. This is a more or less non-uniform one. Okay, so the mathematics of map projections is actually a problem in differential geometry. So it says here, just as I mentioned, that the Gauss curvature of the sphere of radius r is 1 over r squared. And that of the plane, since the plane is essentially part of a boundary of a sphere of infinite dimension, there's a theorem due to Gauss called theorem egregium, the egregious theorem, that says that two isometric surfaces have to have the same curvature, so if they don't have the same curvature, they cannot be isometrically equivalent. So the plane and the sphere are not isometric, so there's no way to map the sphere so that distance is preserved. So you can actually go down here and look at these various equations of parametrizing. But when you go down here to, I think there's a bunch of differential equations that you end up solving. I actually have a Maple worksheet that I'll download in just a second and fire it up. Now there's a nice article here, again in this mapleapps.com, looking at the problem of distortion. And depending on what function you use to map the plane to the sphere, you can think of it this way. If you take a square with Euclidean distance and you try to tear and fold and deform this onto a surface, obviously you can do it onto a cylinder with no distortion. But if you try to put it onto this shape, three-dimensional surface, you can see the distortion that will occur up in these. This is an example of another mapping here. Slightly less distortion, but then near the top, you're not going to preserve the areas. There's another map. These are other maps here. So depending on the different maps, you can have different levels of distortion. And these are a way of trying to put it back onto the sphere. Okay. So let me actually try to download and show you how this whoops. That was not useful. Let me download that as a MWS file. Okay, while I'm downloading and trying to execute the Maple worksheet, I'll look at the PDF file for the geodesics so you can actually see what results. Let's have a fairly robust machine to run this particular Maple. It's very computational. So this explains how to draw geodesics on a cone, and this only uses the built-in Maple command, so it has plots and linear algebra. The first thing it does is it defines an inner product. So if you have two vectors, x and y, if you take the product of the first coordinates, the second coordinates, and third coordinates and add them up, that's just the dot product. So what this does is it inputs a parameterization, and then it computes the partial derivatives of x with respect to u, with respect to v, takes a dot product xu with itself, xu with xv, and xv with itself, and these are E, F, and G for the Riemannian metric. It then simplifies them. Then let's go up here. Then there's the geodesic equations, then take E, F, and G, and write down like the differential derivative of u with respect to t squared, etc. So you can just go down through that. What results is more important. Then there's a geometric plot out of this. So the parameterization for a cone is x equals u cosine v, y equals u sine v, and z equals u. And if you want to parameterize a torus, that's radius 2 from the center and then radius 1 about the diameter, you get that particular parameterization. If you plug it in and end up plotting the cone, these are the geodesic equations. So in other words, you have to solve u double prime minus 1/2 u v prime squared equals 0, and v double prime plus 2 u prime v prime over u equals 0. So you have to solve that nonlinear system of two equations and two unknowns of second order, and you end up getting This is not a very good, the PDF file kind of broke when it tried to grab the graphics. But in the particular case of a cone, you can solve them analytically, and we'll show you that in just a minute. So we can actually compute the geodesic and show that it's shorter length than the Great Circle. So let me see if the Maple has finished computing. Okay, while we're waiting for Maple to complete here, there's a nice little slideshow that I was able to find on the internet. And this explains a little bit about what geodesics are and their importance in computation. So in the sphere, geodesics are all actually great circles. Great circles are intersections of the plane passing through the origin and the 2 points that lie that you're trying to connect. These happen to be the same paths, obviously, that airplanes fly between 2 points because it minimizes the distance, the curved distance between 2 points on a sphere. So, for example, if you want to go from Charlotte, North Carolina to Paris, you actually go over Newfoundland. So when you view it directly above, the circle is straight. Now, the definition of a geodesic is this. It involves this matrix here with what are called Christoffel symbols. It's kind of complicated, but you can see that it involves a second derivative for each coordinate system. So it's a system of nonlinear second-order equations. Now, in the plane, every straight line is a geodesic with curvature 0. And the geodesics on a cylinder look like the following. So the geodesics along the cylinder look in this form, and you can see that the geodesics from, well, these can wrap around and not be closed, or they can be periodic like so. Now, the existence of closed geodesics on the surface was actually a very important theorem. So because the plane and the cylinder are isometric, areas, angles, and lengths are all preserved. This is not true on the sphere. So within any 2 points on the sphere, you can go the short way around, or you can go the long way around, and one is the shortest distance between 2 points, and the other is the longest distance, and the sum add up to the circumference of the Earth. Obviously, you wouldn't want to go from, say, Houston to San Antonio by heading east and crossing over Europe and going 23,000 miles around the Earth. That would not be practical. So general geodesics do not close. And in 1917, David Brokoff, a very famous American mathematician, showed that there was at least one closed geodesic on any deformed sphere with any metric. In 1929, they extended it to 3, and in 1991, actually fairly recently, they showed that there's an infinite number. So these are geodesics along a torus. A torus we know is a donut. And this is the catenoid. That's a very famous curve that has to do with if you take 2 telephone poles and look at the curve that the wire hangs down, it is actually a catenoid. And the helicoid is this propeller-type object here. Now, along the geodesics have very important properties locally along the geodesic. There's no curvature in the tangential direction, and the geodesic curvature coincides with the surface normal vector, and there's a number of other properties that come from just the definitions as well as equations that describe it. If you have a Euclidean metric, it's pretty easy to tell whether something visually is a geodesic or not, but if you have a non-Euclidean metric with different weights, for example, this is a geodesic in a hyperbolic distance rather than the spherical. Now, in general, the shortest path between any 2 points on a surface is a geodesic. and from every point there's a geodesic direction. Now there's some various applications. I'm not sure exactly what fiberglass tape winding has to do with geodesics, but painting, and I have no idea what a tent has to do with the geodesic. Or apparel. I guess cutting things is... So these are some very complicated surfaces called manifolds. This is the representation. And this, again, is the formula. It's a second-order system of nonlinear differential equations, and these are coefficients that come from the metric. And the condition is that you either prescribe the function and the derivative at one point, or you give 2 points. If you saw there was a 2-point nonlinear differential equation, this particular nonlinear equation, 2-point boundary value problem, you'd have to solve it numerically. It's very difficult to come up with analytical solutions. Those gammas are related to various derivatives that come from the metric. And this actually is the language of general relativity. And this basically says how to solve them. So this is the geodesic. If you have a 2-point solver, it then computes these coefficients for the equation, solves it, and then compares the length, and then iteratively tries to find a path that minimizes the length. Okay, so here's some advertisement about this particular piece of software. It uses the Runge cutter, which is a numerical method. Now, it is possible, for example, if you're going over a hill here, that you could have roads that take the same length depending on whether you go over the hill or around the side of the hill. So you could have multiple geodesics that are minimum length. If you have a saddle point region, the geodesics are minimal. That's a negative curvature. So we'll go, I guess, quickly to the end. There's just several more slides here. This is finding the shortest path on a donut. Now it also gives a link, I think, at the very end to where you can get the software. So you can get it at NetLib under Geodesic, or you can get it at this particular company. The last link that we have here is the dictionary or the encyclopedia reference for geodesic out of Wolfram's Math World. Now, this goes through several other links here that I won't go through, but it does have a nice description of the arc length formulation for geodesics. So if you have a surface that's given parametrically by 2 coordinates, UV mapping into XYZ space, what you're really minimizing is the length of the arc, dx squared plus dy squared by dz squared. That's the arc length. Now that comes clearly from the following. It's in 2 dimensions, so this is in R2. If you have 2 points here, by the Pythagorean theorem, this is delta S, this is delta x, and this is delta y. By the Pythagorean theorem, delta x squared plus delta y squared equals delta s squared. And if you have a curve that you want to calculate the coordinate or the arc length from, you can approximately calculate this as a finite sum of these little arc lengths, delta si, say 1 through n. So that's delta S1, delta S2, etc., up to n of them. Now, this is the summation I equals 1 through n of the square root of delta xi squared plus delta yi squared. Now, if I were to parameterize this by x as a function of t and y as a function of t, then this would be I equals 1 to n delta xi over delta t squared plus delta yi over delta squared delta t. Just divide and multiply. And this you can see is just the velocity. So in the limit, this becomes dx dt squared plus dy dt squared square root of that dt between t0 and t1. And this limit just goes to dx squared plus dy squared square root of. So we have two formulas for arc length, dx squared plus dy squared, or the parametric form right here. Now clearly in 3 dimensions, you just add a third coordinate. So you have square root of dx squared, dy squared plus dz squared, or parametrically dx dt plus dy dt plus dz dt dt. Now if you interpret this as a velocity or a speed, then the arc length is just the integral of ds dt dt, or the integral of ds, say t0 to t1. Okay, so it's clear that that's the arc length. Now if you do a little bit of mathematics and say, well, x depends on u and v, same with y, then you get this formulation here. And if you plug all of those symbols in here, you'd get the square root of this big complicated expression, which in general is going to be a linear combination of dx, dy, dz, or du and dv, one of these two formulas. Now, this is where it links into the calculus of variations. This is the Euler-Lagrange differential equation, which I will probably try to derive next time. It's a little bit too complicated to do right now. But the geodesic equations come from minimizing the distance, the arc length. So I minimize the distance dx squared plus dy squared plus dz squared. Between, if I have some complicated surface, and suppose that I have one of these saddle point surfaces with negative curvature here. So it comes down like this. And suppose I want to connect a point on one side of this hump and then a point over here on the other side. So it's clear that the path is going to be some path maybe complicated like this. It's going to go over that rise and connect this point with this point. Now what's going to be true about this path relative to all other paths is if I take any other path, no matter how close by, remember it has to go over this rise, or if I go up here and then go on the other side and then connect here, all other paths are greater. So the geodesic is the actual minimize this over the all set of possible paths. Now the difficulty with this formulation is, of course, is you don't know, well, the set of all possible paths is quite large because you have to parameterize every smooth line or smooth curve that connects these points, compute the arc length on each one of those according to this formula, and then compare all those and pick the smallest. So that's very difficult. But by calculus of variations, which we'll talk about next time, that is exactly an area of mathematics that was built or created to solve such problems. And by that I mean the general problem of the calculus of variations is if I want to minimize a certain integral of a function of, say, t and u and its derivative du dt, if I want to minimize that, I actually get a set of differential equations. I get to minimizing it, I get a set of minimizing conditions, which are called the Euler-Lagrange equations. Now I will talk about these next lecture, but they're very important, and these actually are the same as the system of two geodesic equations. Okay, continuing on, the Euler-Lagrange equations for this are this very ugly set of complicated equations here, but they do reduce to the geodesic equations in the particular cases that we're interested in here. Now, if you have surfaces of revolution, that actually simplifies into this form. And there's a lot of links towards geodesics that you can get here. So the kinds of problems that I'm going to be looking at next time, just to give you a little bit of a preview. So problems in calculus of variations. These are some of the most interesting problems that I know. For example, here's a problem here. If I have a telephone pole here and a telephone pole here, and I have gravity, what is the equation that a wire of length L, and I'm assuming that L is bigger than the distance, what is the shape of the curve that a telephone wire under the influence of gravity will take? So this is the question of what shape a telephone wire will take. Another one is a very interesting problem in roller coaster design, and that is if you go from a point here at some height and you go out a distance here, L, where the height is 0, what is the curve of steepest descent? So what curve gets you down here the most rapidly? So it's actually not the steepest descent, it's the minimal time. So get from point A, point B in minimal time. Now, minimal time over distance will really lead to the largest velocities and the greatest acceleration, so that's, of course, what you want to do in roller coasters. So you can see, I mean, and you don't have any initial velocity here, you just start from rest. You can see if you have a very shallow curve up here, it may take you forever, and then you have this very rapid descent. That would take a long time, or else you might go very rapidly, you know, like those rides where you get dropped out of a tower and then you gradually slow down like this. So these actually take relatively long time, and there's some optimal curve in here that this is actually called the brachistochrone problem. I may not have spelled that right, but I'll describe that next time. Another very fascinating problem in calculus of variations is a minimal surface problem. So suppose I have a soap bubble here. Actually draw this reasonably good. So if I have a soap bubble and I've got a bubble that looks like this coming out of it, that soap film is going to take on some geometry. And the question is what? So if this is a soap bubble, the curvature and forces have to do with each other. And so what you're trying to do is you're trying to find for a given amount of surface area, what is the shape of the surface connected to this boundary that will have prescribed curvature. So, for example, curvature is 0 or something connecting this bow. So you might, now this is called a minimal surface problem. And it was one of the classic problems of calculus of variation. So we've got wind coming in here, and then it pushes this out. What is the shape of the soap bubble? Well, you all know, for example, to maximize volume and minimize area without the influence of gravity, that you take on a sphere, right? So this has maximum surface area with a minimum volume. The same as a square has the maximum area and the minimum perimeter. Is that true, or is that a circle? That may be a circle. Yeah. I have to think right. I believe it's just a two-dimensional version of that. So a circle will have the maximum area and the minimum perimeter. Okay, so these again are problems of maximizing or minimizing something with a given constraint, and that's the study of the calculus of variations. So that's where we're going to lead to next. Now I do want to note that there is a homework assignment. The next homework assignment, homework number 5, homework number 4 is due today. Homework number 5 is just a couple of problems and exercises out of Giller. I may add one more problem here. I haven't quite figured that out yet. But it will not have any epsilons and deltas, so that should make everyone out there in TV land quite happy.